Hello friends, welcome to Ameta Chemistry. In this video, we will discuss some CSIR net previous year questions and we will try to solve them, especially from inorganic chemistry. So let's start questions. The first question is the electric dipole allowed transition in D2 atomic system is. Okay, so the terms are given here. First is 3F21D, second one is 3F21P, and third one is 3F23D, fourth is 3F23P. If we see the option number 3, that is 3F23D. Okay, so let's check spin allowed, spin allowed transition. In this case, we have to see the multiplicity. The rule says that delta S must be 0. Okay, so just we have to check the spin multiplicity. Here 3, here 3. So 3 to 3. Okay, so delta S value will be 0. And that's why we will say this transition is allowed transition. But in case of now we have to see the Laporte allow. For that, so the condition is delta L must not be equal to 0, or it should be delta L should be equal to plus minus 1. It may be plus 1, or it may be minus 1. So here is F. For F, the L value is 3, and second one is D. For that, L value is 2. So if we check the delta L value, so 3 minus 2, it comes 1. So that's why we will say yes, it is also Laporte allowed. So option number 3 is the right option. Okay, now first option, if we check the first option, in this case the delta S value is 3 minus 1 is equal to 2, so that's why it is not allowed. In this case, again 3 and 1, that's why it is also not allowed. But in this case, what's happening? 3 and 3, yeah, delta S value is 0, so that is spin allowed. But if we check the Laporte selection, according to Laporte selection rule, so delta L value comes, this is the F. For F, delta L value is 3 minus 4P, it is 1. So it comes out 2, and that's why delta L value is 2. And rule says delta L value must be plus minus 1 only. So that's why it is not allowed. So that's why option number 3 is the right option. Let's discuss next questions. The correct d electronic configuration showing spin orbital coupling. So first thing we have to remember that for spin orbital coupling, the T2G set must be unsymmetrical, yeah, asymmetrical or asymmetrical. Okay, so just we have to check in which option the T2G set is unsymmetrical. In this case, there are 6, so that's why it is symmetrical. Here is also 6, it is also symmetrical. In this case 3, it is symmetrical, but in this case it is 2. Okay, so in this case T2G set has 4 electron, and if we fill the 4 electron in T2G set, so these 4 electrons can be filled like this, 1 2 3 and 4. So that's why it's asymmetric, yeah, unsymmetrical. So For spin orbital coupling, T2G set must be asymmetrically filled. So that's why option 3 is the right option. Let's discuss next question. That is the term symbol for the ground state of nitrogen atom. So for nitrogen, we have to find out ground ground state term symbol. Okay, so if first we have to see the electronic configuration. So its electronic configuration is 2s2 and 2p3. Okay, so its electronic configuration is 2s2 and 2p3. So it has n value. N means number of unpaired electron is 3. And first we have to find out the s value. What is the s? It is number of unpaired electron by 2. So on what is number of unpaired electron? It is 3. So 3 by 2. So s value is s value comes out 3 by 2. Now we have to find out L value. Okay, L value is summation of M value. Okay, so M value, what is for this electron? It is +1. For this electron, it is 0, and for this electron, -1. Okay, so we have to sum it +1, 0, and -1. So it is cancelled to each other and it comes 0. So we know that if L value is 0, then its term is S. If it is 1, then it comes P. And if it is 2, then it is D. And if it is 3, then F, and so on. So for S value, L value, for S, the L value should be 0. So it is 0. So that's why L is 0. Okay. Now, how do we write the term symbol? We have to write term symbol like this: 2s plus 1 L and J value. Okay. So now we have to calculate 2s plus 1. So 2 into what is S? S is 3 by 2. So 3 by 2 plus 1. So it comes 4. Okay. So we have to write instead of 2s plus 1, 4. Now L is 0. So for 0, we have to write S. So it is S. Now we have to calculate the J value. So J value is given by L plus S to L minus S. Okay. Now what is L? L is 0. S is 3 by 2. From this to 0 minus 3 by 2. Okay. So it comes 3 by 2, then minus 3 by 2. Now we know that it is half filled, and we know that half filled or more than half filled, we have to take maximum J value or highest J value. So highest J value is 3 by 2. So that's why it would be 3 by 2. Okay. So we will write 4s 3 by 2. Now find out this value in option. So it is 4s 3 by 2. So fourth option is the right option. Come to the next question, which says that the complex that absorbs light of shortest wavelength is. It was asked in CSIR 2011. So we have to find out the complex which absorbs shortest wavelength, and we know that short wavelength means high energy, because wavelength is inversely proportional to energy. So that's why when high energy is absorbed by a strong field ligand. A strong field ligand. Okay, so just अपने को क्या करना है? We have to find out which ligand is the strong field ligand. Fluoride, it is weak field ligand. Cobalt, water molecule, it is weak field ligand. Okay, NH3 it is a strong field ligand, and oxalate it is also a little bit a strong field ligand, but as compared to ammonia, it is weak. So that's why option number 3 is the right option. Why? Because it has ammonia ligand, which is a strong field ligand, and because it is a strong field ligand, that's why it will absorb high energy. And if it is having high energy, then its wavelength will be shorter. So that's why option number 3 is the right option. Now come to the next question, that is for high spin and low spin D6 of octahedral complexes, ML6, the generally observed spin allowed transition respectively. Now we have to find out the spin allowed transition. So the atomic configuration is D6, and we have to find out for low spin as well as high spin. Okay, so now first we have to draw low spin as well as high spin. So I'm trying to draw here low spin complex. If it is low spin, then 1, 2, 3, 4, 5, and 6. Okay, and if it is high spin complex, then 1, 2, 3, 4, 5, and 6. Now we have to check whether how many spin allowed transitions will be in high spin and how many spin allowed transition will be in low spin. Okay, so here two orbitals are available. So this electron can go here and this electron can go here. So it will have only two spin allowed transition. In this case, this electron can go, only this electron which is in opposite spin like this. Okay, so this electron can go here and it can be adjusted like this. Okay, so that's why it has only one spin allowed transition. वापस समझ लो इसको, because in case of high spin, one electron's spin is this, another electron's spin is this. It is in second orbital, it is in third orbitals. Now upper level, yani ki EG orbitals, there is one electron and there is also one electron. So this electron, this type of electron having positive spin, it cannot go here. If it will go here, then it will be like this and it cannot be possible, right? So only this electron will go here or here. So only one transition will be occur. So that's why in high spin, one transition, low spin, two transition. Okay, so respectively, first it is asked for high spin. So for high spin, only one transition. So that's why this is the right option. And for low spin, it is two. So hope you like this video. Please subscribe the channel. Thank you very much for watching this video. Thank you.